Alright, so one thing I am going to tell you is we have a project that's tied into this this presentation. Remember how I said we don't have hot reports anymore the rest of the year? Okay, well now this is what's going to replace it. You guys are going to have a project that's basically going to be, I'm going to give you an accident scenario. You are going to have to calculate who, if anybody, is at fault. I'll give you more information later. Who, if anybody, is at fault, and you are going to have to write a presentation, basically, in which, if I were to put you on the stand, this is what you would say, okay? You guys are literally going to be taking the role of these officers, and you are going to be presenting that to me. That is going to be your final project. Seniors, you are required to do that one. There's one more that I will talk to you about later, but I don't want to take time away from these gentlemen, so I will talk to you guys about that one later. I will give you more information on that. But because of that, we just started energy. We just finished friction. We're going to finish energy and we're going to get into momentum, power, work, things like that. So that means this is going to be stuff we're going to be learning. They are going to flat out give you some of the formulas that you can use to calculate this for your final project. So I strongly, strongly, strongly recommend taking notes. You know my rule on notes. I don't grade them, but I strongly recommend it. And for that reason, I'm giving you page 83 in your notebooks. Okay? I would take notes because you can use these notes for your project. Alright? I'm going to go ahead and turn it over to Officer Lawson. All yours.
Good morning.
Good morning. That's
My name is,
I can't hear you. You can't get him to shut up any other day.
Morning.
My name is Sergeant Jeff Lawson of the California Highway Patrol Central Division, multidisciplinary accident investigation team. I'm mate. My team consists of all the blue-clad gentlemen over there against the wall. Starting from the front of the room and working backwards. That's Officer Robert Shaw, Officer Mike Wright, Mr. Dan Haas. He's a senior engineer with Caltrans. Senior not because he's old, senior because he's been doing this for a long time. He's promoted up. Mr. Kevin Weaver. He's our motor carrier's safety specialist. He's in charge of all the commercial vehicle side of the investigations, as well as our mechanical inspections. Next to him in the gray hair is Officer John Coulter. And the smiling one with his hand on the bookcase is Officer Joseph Machado. We've got probably over 50 years of experience on this team. Those of us that are officers wearing gun belts, we were hired as regular CHP officers and we wanted to get into this line of work. Each one of us, including the non-officers, have a dedication to the investigation of high-profile cases, cases that the regular CHP officers are not capable of solving, officer-involved shootings, aircraft accidents involving our departmental aircraft, similar to the National Transportation Safety Board. We take a significant amount of schooling over and above our CHP training. Each one of us has spent, what is it now, Mike? How many weeks? 8 weeks? Yeah, about 9 weeks of additional training, 8 hours a day at Resident Academy up in Sacramento to get to the level of investigative skills we have now. Problem is, once you're trained, you've got the info, but now you need experience. So we've got a very experienced team. We're responsible for investigating these accidents that occur from the top end of Modesto, or just before you get to Stockton, all the way down to the top of the Grapevine, from the coastal mountain range over to our side of the Sierras. We're on call 24 hours a day, 7 days a week, 365 days a year. So hopefully we don't get a phone call, otherwise we're going to have to split the team and disappear and go do our thing. I mentioned high-profile accidents. By that I mean high media attention. How many people were listening to the news? Was it last Thursday where they have the vehicle that crashed into a fighter jet over at Navy Station Lemoore? Nobody listens to the news. Great. Anyway, we got called out to work that one. in the Greyhound bus crash in 2010.
What about Paul Walker from Basil Bridge? Are you know who he is?
In that crash, Officer Coulter was working for the Southern Division 18. So that's the kind of stuff that we do. We use various types of equipment. We use survey equipment that shoots a laser.
Oh yeah, sorry, that one's
It
lower.
shoots a laser and gives us distances, and it'll work from about functionally 500-600 feet, if not more. We took a couple of shots at the F-18 crash that were 900 feet. We've got a three-dimensional laser scanner. I know you guys have seen those on TV. They give you a point cloud. We used that yesterday to profile the vehicle for some crush measurements. We're pretty much at the cutting edge of, I want to say this with a smile on my face because we've got some more equipment to purchase, but pretty much at the cutting edge as far as law enforcement, measurement, and evidence gathering techniques, technology, and equipment for the state. There's 8 teams like us spread throughout California. So we're one of the larger teams, but functionally you're looking at, there's only about 40 officers that are trained to this level. So, and that's within the state. And nationwide, I think there's only one other state that's doing it full-time like we are. So it's a pretty select group of people you've got in front of you today. I've got a crash dynamics diagram up here on the board. The way we work, you're looking at vehicle dynamics analysis. When we get out there to the scene, we only see these tire friction marks. We see the damaged vehicles, the bodies out in the roadway, and the vehicles are at their points of rest. So how do we reconstruct that? We basically have to work backwards. And this is where your friction training comes into play, what we'll be doing today. We can quantify the amount of velocity that this vehicle had when it went from impact to rest using some equations that we're going to show you. We use the conservation of momentum, typically in a crash like this, to give us our speeds at impact. And then we use work energy theorem again to figure out how fast this truck was going at the time he started laying down the entire friction marks. This particular crash involved a Volkswagen Jetta driven by a young female who was under the influence. She went to get on the freeway, lost control, began to spin out, crashed into this concrete bridge rail, came to rest. She got out of her car, yeah, that was lucky, didn't get hurt. But she failed to recognize that she was in the fast lane, and this is a federal fire department pickup truck. He skids into her, squishes her between his front bumper and the Volkswagen, and she ends up dead out here in the street. So, 2 takeaways from this. What's the first takeaway?
Okay.
See what? Don't drive under the influence. Outstanding. What's the second takeaway?
Yeah.
Well, how about we stay inside a car? Okay? Because an auto versus pedestrian, the auto's going to win every time. If she had stayed in her car, she would have been hurt, most likely, but she probably wouldn't have been dead. So if you guys get in a wreck, stay in your car with the seatbelt on, because as Mike brought up in the last class, they still work even if your car's crashed. Okay? And they keep you inside, and we don't drive dudes. Mike and Dan, they're going to introduce you to an equation that we're going to be using today. Pay attention, because they may suck one of you out of the group. We'll help them out on the board.
Okay, as Sergeant Lawson was describing on the diagram here, he referenced these 2 marks here and called them tire friction marks. It's typically what you would call a skid mark. And they're caused by when the tire is no longer rolling on the road, and it's locked, and it's sliding across the road. That sliding there is generating friction, and the force of the friction that's actually slowing the car down. So the force, we can apply that towards the car. We know that force is equal to mass times acceleration. The car has mass. If you apply a force to it, it's going to accelerate. If you apply the force in the direction opposite that the car is moving, the car is going to slow down or decelerate, negative acceleration. When we look at a car that's moving, it's got kinetic energy. And there's an equation for kinetic energy. I'm not sure if you've gone over it in class yet. But the kinetic energy is equal to 1/2 mass of the object times the velocity squared. Okay. We also know that the work done on an object is equal to the force applied to that object times the distance through which that force is applied. And in the case of cars sliding down the road, the force is the friction force acting upon the tires of the vehicle. Let's see. Okay, so we can calculate the force of friction if we know the weight of the car and the coefficient of friction. So the force applied to this car as it's skidding is going to equal its weight times mu, the variable that we use for coefficient of friction. Now going to the equation above where work is equal to force times distance, I'm going to take that W times mu, or weight times mu. Oh, he broke out the weight to mass times gravity first. Weight is equal to mass times gravity. So the next thing we're going to do is we're going to, now that we have this, we're going to take this F and we're going to substitute it into this equation up here, figure out the work that's done on this car to bring it to a stop.
And the energy is neither created nor destroyed. So in conservation of energy, the energy, in this case, which is the energy from a moving object, and we know that is called kinetic energy, is equal to 1/2 mv squared. That is equal to the work it can do in being brought to rest. And that's why how we solve this is by setting KE equal to work. And after that, it's just algebra, and we'll get to the equation for how we determine the speed.
So he's going to substitute 1/2 mv squared for the KE. He's going to take this force times distance, substitute the mass times gravity times mu, force up here, and then multiply by distance, and that gives us 1/2 mv squared is equal to mass times gravity times mu, the coefficient of friction, times the distance. And I think he's just isolate for v squared. He's going to get rid of the half by multiplying both sides by 2. And we've got mass on both sides. They cancel out, so you can just get rid of them. And then he gets an equation, v squared equals 2 times g times mu times d. Take square root of both sides, and that gives us an equation that we can use to calculate the velocity of a vehicle based upon gravity, the coefficient of friction, and the distance that it slides.
I have a quick question for you guys. Now, they just did a bunch of stuff on the board, all right? And what they do is in the real world. So they go to court, they testify, they determine fault, so on and so forth. Did they use calculus?
No.
Did they even use geometry? This is basic algebra, right? You've got two things used there. You have algebraic manipulation and you have substitution method. It's the only things they used. So while at first glance it's, oh my God, all the letters. When you stop and look at it step by step, guys, it is that basic. And like I've told you all year, don't overthink it. This is step by step. They just showed you how they came up with the equation. Okay? Now you know where it comes from. So don't panic when you see this stuff, and don't panic about it on your projects, okay?
And as Mr. Haas wrote on the side over here, mu, the coefficient of friction, is unitless because it's basically a ratio. The units that we use for our calculations in our field, we use feet, feet per second squared. So for gravity that we're going to use 32.2 feet per second squared. You typically use meters per second squared, right? 10 meters per second squared. We're going to be working in units of feet. So the gravity constant that we're going to use is 32.2 feet per second squared. So write this down, you're going to need that.
We're gonna be doing some calculations out there in the second half. So when they say write it down, put it in a spot where it's gonna be easily retrievable.
Put a box around it.
Write this one down, you're going to need that. We're going to have a conversion factor over here that we use. Now your speedometer on your car is calibrated in miles per hour. We're talking about feet per second. You know, if we wanted to measure a skid mark over here that's a certain distance, let's say it's 80 feet long, if we wanted to measure that in miles, it would be a very small number, very difficult to measure. We don't have rulers or tape measures that's calibrated in miles. So what he's doing is he's writing down a unit conversion or dimensional analysis that we use to convert miles per hour to feet per second. And the 3600 just comes from, because we're going to go from, in miles per hour, we're going from hours to minutes, minutes to seconds, so that's 60 minutes in an hour, 60 seconds in a minute, 60 times 60, 3600. The 5280 comes from that there's 5280 feet in a mile. So we can use this equation if we know the coefficient of friction, the distance that the car skidded, gravity we know is constant. We can calculate how fast the car is going. Another thing that we can do, we can rearrange this equation. If we know how fast the car started, we know gravity, we know the coefficient of friction, we can figure out, okay, how long is it going to take this car to stop? So what we would do is we'd rearrange this equation, or this one, to isolate the variable d for distance. So is there somebody who can come up here and volunteer?
You don't go, I'll call
Just take
someone.
someone.
I got the phone up.
Maybe
ready.
the last classes.
Somebody in the last class, yeah, she does.
Yeah.
We'll
I don't
have
have
you
any
through,
more
we're not gonna
Cheetos.
leave you hanging.
Somebody volunteer.
We'll talk you through it.
It's out.
There it is.
All right. Someone who raised their hand this time. Thank you.
Okay, so we can either start with this one or this one. This one, if we start here, we've already gotten rid of the radical. It'll probably be easier to start with this one. And just use this one right here. So let's just start with a clean spot right here. You can start right here. Write down v squared equals 2g mu times d. Okay. Now, we want to isolate d. We want to get d on one side of the equation. So how are we going to do that? We don't have to take square root because we got rid of the radical. We don't want to use the radical. So I took it from this step and I actually went backwards one. So we're going to start with this one here.
So don't
So,
overthink.
to get rid of, this is all multiplication, all right? If it was addition and subtraction, you could just add it to both sides, subtraction to both sides. But since this is all multiplication, how are we going to get these variables, the two that variable? How are we going to get these to the other side of the equation? Divide it. So let's take this v squared, divide by 2. Divide both sides of this equation by 2. Okay, these two are going to cancel out. So that gives you v squared over 2 is equal to g mu d. We do exactly the same thing with.
It's a G, that's a 2.
Oh, was that a g?
Yeah.
Okay, it looked like a 2.
Yeah.
Right, there we go. All right. And we're going to do the same thing. We're going to divide out. We're going to get rid of all of these variables, get them all onto the other side. So the D is isolated just on one side, so that we can use it that way. So go ahead, do the same thing with the G.
Can I do both at once?
Yeah, do both at once if you want.
So is it gonna go under the 2 or next to the 2?
When you divide something, aren't you multiplying by the reciprocal? So all you have to do is just move it to the bottom. So we move 2G to the
So it's gonna go right next to
G mu to the 2.
He writes his G's weird. I have to remember that when I create G.
Okay. Cancel out G mu. All right, and that leaves us with B squared over 2G mu is equal to D. So we can use this equation if we know a car is going 25 miles an hour as you drive it down a residential street. How long is it gonna, what distance is that car gonna travel to come to a stop?
So, we want to write down
This one?
this one over here. Thank you very much. Outstanding job.
Hunter, are you here?
So when we go out there, we're going to be using these two. Okay? And then the conversion from feet per second to miles per hour. Everybody got it? Okay, you got calculators or phones that we can calculate on? We're gonna go out to, I don't know if you guys saw us setting up when we came to school on the south side of this parking lot over here. There are cones set up. Initially walk over to where the cones are grouped, between the cones and the curb. We'll run through a couple things. We're actually gonna measure the friction of the roadway. No, are we coming back here?
We will, yeah. Hey, you don't need anything else. Okay, are you here? Go back. I'm trying to find a few key people. Zach's here, right? There's someone not here today. Zach's not here? He's right there.
No. Okay. All right.
No, that, the stuff we're doing there.
Leave it the same.
I like to reiterate, because a lot of these kids, I do the math for them, their equations, and they overthink it. They think they have to do those complex derivative equations and finding limit. It's like, no, guys, remember, and showing them that you're doing basic algebra and not doing the complex basic equations.
Oh, it's still recording? Yep. You're gonna edit this later, right? Uh-huh.
That they're overthinking crap.
Go underneath this page, guys.
Guys, we're going to the left. We're not going to the back. That's the Spanish club. Sorry, you're not going back there. You're going to the left. Even though I know you love back there because they're doing tacos. Under the tape, under the tape, under the tape. Great action.
Somebody got food over here. Driving a car.
Yeah, they're making tacos over here. Yeah, it's
Measure friction.
Yep.
By the way, an instrument we have in the
Got the
vehicle.
liaison right there.
The old method was used what's called a drag strip. This thing was made at some point before I was born. Says 30 pounds. Are you serious? Now our volunteers, we're going to demonstrate it first. You have to have a level pull right here. This has to be level. We want the actual force and resistance of the road against the tire. Okay? So we're going to pull it level. Two of the volunteers are going to be looking at the scale to tell us how much force it takes to pull. Okay, let's reset and let's let these guys do it. Typically, we'll add C. We'll do this at least 3 times. To get a good average, to get a number, to get like 22, 22, and 19. You guys, go ahead. Look at this scale. I'll show you what we're getting.
Both look at it and decide, okay, what's the pull force that he's actually doing. And the person that's pulling, you want to pull it at a constant speed. Okay? You don't want it starting and stopping. You can see a lot of bouncing in the middle. It's hard to read. We don't want you to be accelerating it. Lower. Let the wheels roll. There
What you got? What you guys get?
22.
22? What did you get the last time? On the left?
23.
23? 3 more volunteers, quickly. All right. All right, new group.
Keep the person ladies coming out here because she would love.
Thank you.
You're going to watch the video on here, and you're going to see what number is the needle point to.
Down lower. The wheels gotta roll. Perfect.
Why is it important that they pull horizontal to the ground? It's a normal force. You're applying upward pull on the force that has some horizontal and some vertical. If you're, let's say you're on that pull force, one pound of that is being used to lift that higher up. You no longer have to stay 30 pounds. So that's why it's important. Pull these things horizontal. So we don't,
What'd you get?
22. 22.
Okay, so the whole weight is 22 pounds. 30. We're gonna do the first skid test.
so now that
The cameraman needs to be
we've measured you basically, the variables that are in those equations that we gave. Like gravity, we already know. So we've got mu and gravity. We know one other thing. We can solve for the other unknown. In this case, we are going to measure skid marks. So D is something that we can measure. The velocity is something that we'll calculate. If we knew the initial speed of the car with the mu that we've measured, you can figure out what is the stopping distance that that car needs to skid to stop.
And then the gravity just
So they're just gonna drive and slam on the brakes? Yep. Drive and slam on the brakes?
right backwards, forward.
No, they'll drive back and then they'll keep on accelerating. Yeah.
Oh, are they gonna start at those two cones and just like floor it until they get here and then slam on the brakes?
Yeah, they're gonna go back all the way.
They are.
Look at it.
Right.
Back.
Yeah.
You need to be off the cement.
Gotcha.
What's up, dude? What's up? Do it. I'll flip it, man.
Run it in slow-mo if you got it on your camera.
I'm just joking. I'm stopping.
Wait, we're not starting yet, right?
No, I'll tell you what. He's answering a question first.
Damn it. Second.
Front one, right? Yeah, it's in the back.
So what I want you guys to do, the physics class specifically, but everybody, somewhat quickly. We're gonna go down this way, circle back around, so where you can see these tire friction marks. Come on.
I want my physics class in between the cones. Okay? Or like right by those cones. Everyone else can kind of circle around it. Malin, get up. I want you more on this side.
All right.
Okay, you're gonna kind of be separated.
Gotcha.
See it, so come on over, man.
Come on over, guys. Come
on,
on.
I have a tendency.
I like to take priority. Sorry.
It's a really smart idea.
They have to do math.
No, it's kind of true. So this.
So now they got to make. They know the coefficient for the drag. Now they got to figure out how fast they are. I mean, they can take your word for it. You ask Josh, I'm going to say he was doing 20, but every time I see him driving, he's doing 80. Oh, on that note, we're going to have these guys figure out who's telling them.
The whole team will look at each item of physical evidence.
Step back.
That now is going to be the beginning of the tire friction mark. Alright, well we're measuring the distance to the pump. The mark that he's measuring is the straight or the curve. Which way is the curve? That's probably due to getting the water on the pump. Okay? So if the front tire was locked, meaning it's not rolling, it caused that car to go to the left. Exactly right. Here I am in physics class. Hi, John. Now, Sean told me
Yeah, can you go at the beginning again? I'm sorry.
that when he put on the brakes, he actually turned the wheel to the right. Okay, so I heard a lot of folks saying you lost control. When you are in a curved roadway or you think you can turn by slamming on your brakes, you don't have any anti-lock braking in your car, are you going to turn? Absolutely not. You lose the steering control of that front tire. So when we go to the academy and they teach us how to drive at high speed, we're coming into a real sharp 90-degree left-hand turn. I believe it's 70? High speed? High speed. We have to make that corner at a certain minimum speed. It's impossible to do it. Standing on the brakes, you're going to skid right through the corner and right over the center. The takeaway from this is we don't turn and brake at the same time. Get off the brakes. Brake first, turn. Alright? What kind of a distance? Distance.
66.5.
Okay, consider this close. 66.5.
Let's see what they're doing. Wait.
Introduce Officer Ferris, Officer Woodrow. We're part of our improvement unit for the highway patrol. We're going to be handing out some information on our Explorer program.
Who's interested in joining law enforcement after 19, is what we say. So, who needs one? Can I just try to give it to you guys? You guys drove them? Okay, so what this Explorer program is, it's an entry-level program before you come on the department as an adult. Okay? You guys listening? are still gonna go through a mini background. Okay? But what this tries to do is prepare you what you're gonna come on when you're old enough to apply with us. Which is you're gonna be held accountable for some of your actions. Okay? Drugs, friends, things that you do not realize that can come to haunt you. Okay? If you're 21 years old and you apply with us, we go back 10 years. So we're basically seeing what you've been up to since you were 11 years old. Okay, and we all know that high school is fun. This is where you get your memories. But just remember, some of those memories may come back to bite you. You know, just pay attention. We're not telling you to not have fun, you know, enjoy your high school years, but don't do stuff that you're not supposed to. You know, we tell you guys all the time, you've heard it over and over, you see it on TV specials, stay away from drugs. Have fun. Remember your year. Don't let it be foggy. Okay? Watch your driving record. Because even though you guys think that you've been driving since you were 16, 17 years old and you come on with this and you have a driving history, well, we don't take people with bad driving history. Okay? We want responsible behind the wheel, not reckless. Okay? You actually can stay on as an explorer until the max age of 21. That's when you age out. But again, we try to get you in your 20s just so if you're going to start our process, we can get you to apply. Okay? Because our process, if you come on with us, is about 18 months. It takes that long. But in the meantime, you can join something like this. Now, if this is something that interests you because you want to give back to the community, you want to do volunteer work, this also looks excellent on your college application. It's because this is a volunteer program. And it's licensed by Learning for Life. And Boys and Girl Scouts of America. Okay? But there are four folks in Roseville. There's one in Madera. I don't know how far you guys live outward or what's close or what not. But they're always taking explorers because we have kids that filter through these programs. They age out and then, you know, now what? So definitely entertain this thought. It's good. It's a good program. You get to see what we do once you pass a certain level of participation. There's like 4 levels. 1 and 2 are in the classroom, so you're going to learn a little bit more about the room. Level 1 and 2 start doing ride-along classes. You guys can do as many ride-along classes as you want. You know, day shift, graveyard shift. If your parents give you that permission, go on a graveyard ride-along. It's awesome. Okay? But that's what I have to say. You guys have any questions for me really quick? We do not have a lot of females on this department. Okay? A lot of you think that we're out there. We didn't think about it. You didn't think that we're not. Obviously, you know there's a height limit. Okay? But it is possible. And it is an excellent career. Okay? Just because you're a girl does not mean that you cannot do this job. Just because you're not physical right now doesn't mean you can't prepare. Okay? But definitely do good in school because we pay attention to your grades as well. So be good. Any other questions? Cool. That's what I do. It's all mine.
Remember how we in the classroom on the right-hand side, we had on the top 3,600 seconds and on the feet 5,280 feet. You have to multiply by 3,600 and then divide by 5,280. That'll convert it into miles per hour. 30 seconds. 37.8.
3 or 4 still rolling.
Oh, really?
Slower, kind of like an Infinity. They never. But it was probably about right here. I cranked the wheel.
Okay, so we've got it built. Okay, guys.
So what I want to do this guy come in 35 miles an hour. Speed that Officer Shaw was driving was 40 points up the road, about 40 miles an hour. There's a reason why your numbers don't reflect this. We're instrumenting what this car's restriction values. Always going to be a little better measurement than that rack.
Plus, they're also only measuring the distance and the tires. There's a certain distance that the car travels from the point that he actually touches the brake pedal to the point that tire goes to the wall.
Tell me, how far is this car going to slide? If I'm going to stand at your measurement, it's going to be right.
You guys are the ones who calculated the 52 feet, the whole class. Because it was multiple people saying 52 feet. If you're within 6 inches, I give you 10 points.
Right, we did the count. We come up with about 52 feet. Hey, what's the only variable? I don't know. What could possibly go wrong?
Guys, you listening? Yeah. Well, no.
Yeah, I did hear it.
We'll find out.
What else could go wrong?
What can go wrong in this, guys? Think about it.
Like, what's this?
Well, what's something
It
can happen?
doesn't brake right at the cones,
Is that going to stop on the line?
okay?
Of course not.
No, it's got a human element to it,
Tire
right?
is not frame perfect.
So,
Human error.
he's asking for your lane.
Oh, wrong. Like if they don't stop right at the nose. Oh, she's doing. Pushing down the street. Straight home. Are you kidding me? Are you? Oh, I want to read him.
He didn't want to hit his super.
How hard he brakes.
How early did it start?
Too early.
Oh, he only hit 32 miles an hour.
This is key variable, man.
Tires are getting warm, so we're probably picking up a little bit more friction.
What was the distance? You said 52 about. What'd you get? I got 31.2. Gotta go fast. Still in advance. Still in advance.
Look, 35.4 miles an hour.
Hey, there's a 24. Hey, we're on the way.
All right. Well, I can see John's face. He had a big old grin on it.
Okay, that's more than 6. That's more than 6 inches, but we don't know where he started.
Okay, so we've done 2, 35 and 40. Now, what we didn't tell you, did anybody figure out what we did to this car to make it slide?
The wheels, tires.
We did some on the wheels.
We disabled the ABS system, okay? Because this thing would be worthless to drive around with no ABS. We'd be skidding into everybody, okay? So your cars, most likely, if you drive a car that's newer than about a 1998, 99, is going to have ABS on 1 or more axles. So now what we're going to do, put the ABS back in, just it's a fuse. Then we're going to do the same exact test, same exact speed, same braking point, but we're going to bring it in at 40. And you guys, the first one that we measured, will show you how much more effective that ABS system is. Because it keeps the vehicle's tires right on the cusp of static friction and dynamic friction. Okay, you guys went over that in class, right?
Nope.
Kinetic instead of dynamic.
I'm sorry.
We use the term kinetic. Remember which one's greater, static or kinetic friction?
Kinetic. Static. Static.
Static, because it's locked in.
Think about it. When you've got a table or a refrigerator or something on the, you want to slide across the floor, it takes more effort to get it moving than it does to keep it moving. To get it moving, you have to overcome static friction. Bob, let's go ahead and redo the ABS. And then bring it in at 40.
Might get your extra credit.
Wow, I got a little light over here.
With her. She took her group, and I let 3 of mine go over there.
Now there is a chance that this may not work. Sometimes the ABS modules don't like to be messed with. So how would we know if it worked or didn't work? Yeah, it won't skid. It won't skid. Now you're going to hear it chirping. And watch that front tire, okay?
See that?
You're going to see it, you know,
Front tires
trying to
stop.
reset it.
You recorded that test.
I'm actually,
You recorded that one that he was in front of.
Yeah. Is he gonna do it again?
Did you see they did a donut? What?
Oh, seriously, these two people.
We got a donuts. Can't How do you set the ABS? I don't know. Yeah, I think he was testing if it's on. Yeah, he was. How do you reset it? Okay, so that's all I need. Because I knew it was something.
Here we go. Oh, I gotta get off.
Okay, alright, sorry. Like, just check out the views. Look at the shuttle, guys. Look at the shuttle.
Oh.
did you hear that?
Yeah.
Skid, release, skid, release. Could you see it in the rotation of the tire? Or no?
Yes.
Okay. So I think he braked a little bit later than he typically does. And then typically what we may or may not see on roadway evidence is a very light gray tire friction mark, which we refer to as impending skids. And that's caused because that tire is slowing down at a faster rate than the vehicle is. sometimes we'll see a short skid and then a gap of nothing and a short skid.
Yeah, you can see a little light and dark.
Want to shift left or right?
My problem is a little bit.
Nice.
47.7.
We have residents and if necessary.
What'd you end up with, Bob? 64.6 feet.
You lost your extra credit.
Can't compete, man.
A friction value for the car of 0.865. So way more better, right? Okay, and we stopped 8 feet shorter than without ABS. Okay, so we decreased the stopping distance from 66 to 58 feet. Okay, so that's also an improvement. One of the reasons you're not seeing a gigantic decrease in stopping distance is the brakes are really hot by now when we start to lose a little bit of efficiency. Any questions? Do not, I repeat, do not do the math, stand in front of your buddy and see if he can get his car stopped before he gets to you. Because what you don't know is that I am standing in a location that looks to you like I'm going to get run over. Because of your depth perception, I'm actually, he can't get to me, okay? I'm not that stupid. I don't trust him. Okay? So, ABS, good thing. If you see that ABS light come on your dash when you start it and it stays on, what do you do? Well, you're not moving, I hope. Tell your folks, if you have to drive it, be aware you don't have ABS. Something's wrong. When you get in your car and you put your seatbelt on and the airbag light comes on momentarily, if that stays on, what do you do? I wouldn't drive. If something's wrong with your airbags, something's wrong with your seatbelts, you got to get it checked out, okay? Any questions? Thank you for your attention. This is a blast for us.
All right, thank you much. Okay, 0.79, we're gonna use that friction value because that's the one that we calculated, it's the one they calculated before we did this final test. Okay, I want you to calculate, if you had a stopping distance, if we measured and we came in and there was a stopping distance of 73 feet, that's what I'm giving you. I wanna know how fast it was going. 73 feet, how fast was it going, okay? You need to tell me how fast it was going. Your homework over the weekend is to calculate it using the information we know. I want the friction value of 0.79, and I want to know how fast they were going down to the second decimal place, okay? Second decimal place. Got it? Bring that to me on Monday. With that, you guys